from the definition of shear and moment diagram, and also the designer's sign convention for internal forces and external losses. So let's set a differential slide dx in that beam got through the distributed load W as I show in the dx there. So let me zoom in and draw that differential slice. Differential slice to the beam as shown. So let's zoom out that slide. We have that beam and the distributed load cut through the distributed load W. And then, of course, when you cut that, let expose the internal forces for that portion. And when I consider that differential slide dx, as you can see, so it is exposed to the left and to the right with the internal shear and internal moment. So let's consider the left side, and I assume the positive shear. So as you can see, create for the shear positive on the left, it have to be going up to create a clockwise rotation on that differential slide to be positive, so that we call V. And for the moment, the positive, it will create a tension in the bottom, so that is the positive moment that we have based on the designer side convention as we discussed. And the other side, the shear have to be going down to create a clockwise rotation on that differential slice to be positive shear. And the moment, as always, and V, as you can see, it may not be the same as the V on the other side. So I got that V plus dV, the change in the internal shear from left to right of the differential slide. Similarly, the moment, it will be positive, it create a tension in the bottom and compression on the top, and it will be M plus dm. And because we don't know the direction of the moment, so we just, or the shear, so we just assume the positive shear and positive moment in each section that we cut. So that what we have in the differential slide on the external load, in this case the W, and the internal resistance forces, shear and moment on the left and on the right. So with that, let's talk about the shear from that differential slide. So let's talk about the shear. What do we have for the shear in there? So let's sum up all the force in y direction. So let's put the x and y for that differential slide. So let's sum up all the forces in, let's write out here, sum up all the forces in y direction. Going up is positive. So what do I have? It have to be equilibrium, so it goes to 0. So from left to right, and you can see the shear V on the left side, and then you will have that differential slide, the distance here is dx. So from that, the distributed load times the length, it become the load, right? So it will be plus distributed load times dx to get the equivalent concentrated load. And then to the right side, we can have VdV, and in this case it's going down, so it will be negative. So we have negative V plus dV. And as you can see from there, it V minus V, so you can see that is 0. V minus V, 0. So from that, I can have dV negative But on the other side, so I have dv, simplify that equation, I have dv equal to w dx. W dx. So if I divide or time 1 over dx both sides, so we will have dv over dx equal to w. So what do I have in there? dv over dx. So as you can see, dv over dx, dy over dx. So that basically the first derivative of a function. In this case, the share equal to something. The first derivative, if you recall, that is the slope, right? Slope of the share diagram. And then, if we continue for that one, dv w dx, that I take integral on both sides, I can also have dv equal to w dx, and let's take integral both sides. Integral both sides. So what do I have on the left side? It will be equal to delta v, the change in the share. On the other side, as you can see, it actually the integral of w dx is first integral, and you can see that is the area. And in this case, w is a function distributed load. Then it will be the area under the load curve. So let's write down there. So the change in the share equal to w dx. W dx. So that two equations that I can have the node for the share diagram. So let's talk about the node number 1. But very important node number 1 here. From the delta v equal to integral w dx. If you already know w dx integral, it will be the area under the load curve. Area under the load curve, regardless of how distribute that load is. So we can say that for the delta v equal to integral w dx, I can have the node is the change in share. It will be equal to area under load curve. Load curve. So that is from the delta v equal to integral of w dx. The second node that I just mentioned briefly earlier, and I want to realize here so that we can have a node. We have delta v over dx equal to w, delta v over dx. Basically, that is slope of the share diagram, because that, remember, dy over dx, right? So we can have slope of share diagram, equal to magnitude of load. Slope of share diagram equal to the magnitude of the load, because that magnitude here, w, as you can see, so dv over dx, it will be the magnitude of the load for the slope of the share diagram. dv over dx equal to w. So those are the share. And now let's talk about the moment. What happened to the moment? So let's talk about the moment on that differential slide. So let me call the point on the right side of the differential slide, point O, and I want to take moment about that point O. Take moment about that point O. So what do I have for that moment? Take moment about O. What do I have here? So sum of all the moment about O, assume counterclockwise is positive. So what do we have there? We have on the left side, as you can see, we will have M, and in this case, negative, M. And then on the right side, we have M plus dm, and it counterclockwise, so positive M plus dm. Okay, and then for the distributed load, as you can see, it equivalent concentrated load W dx in the middle, and in the middle it means half of the dx, so it will have a W dx square over 2, right? If we talk about this, you have a concentrated load equivalent here, and the distance from here to there is dx over 2. From that, we will have the moment about O. It will be W dx times dx over 2. So from that, let me erase that to make it clear. As you already know in statics, so we can have that equal to, and in this case about O, so it, as you can see, that load create clockwise rotation, so it will be negative W dx square over 2, dx square over 2. And then we have the V on the left side times the dx. It will be moment, and in this case it will be negative because clockwise rotation, the V on the left side, and you can see about O, so V dx. The V plus dV go through O, so it's 0. It don't have it in there. So you will have it negative V dV due to the internal load V on the left side. The V plus dV on the right side is 0 because it goes through the point O that we take moment about. So from that, what do I have? I have here negative M cancel out. And you can see now you have dx, no, V, let's write that here, V dx, not V dV, because that is the distance from the left to the right to point O, so dx. So as you can see, compare between d and dx, that dx square differential slide very small compared to dx. So we can make that it's about to be 0. That is about to 0. Why? The differential slide just give you one example. Okay, so if you have, for example, here, and I will erase, if I have dx equal to very small 0.00 inch with that differential slide, what do you have for the dx square? Dx square will be 0.001, and that will be 0.00, then another 20 inch square for the dx square. And as you can see, compared to that 2, dx square very small. If you add those two, it's about to 0.001. So that when you have very small number, then you power that, add them to the original number, it's about the same as the original number dx in there. So with that, we can, relative speaking, the dx square is very small compared to dx. So with that, we can cancel out on the 0, negative m dm. So I can rewrite the equation at a dm equal to v dx. So that's something we want to talk about. So as you can see, similar to here, dv equal to w dx. Now we have dm equal to v dx. So just replace the v with m and w with v, as you can see between those two equations. So I will do exactly the same from here. I can have dm dm over dx equal to v. And similarly, if I take integral of dm equal to v dx with the integral, then the left side become the change in moment, delta m, and the right side basically the integral of the v dx, basically the area under the shear curve. So we can write down here v dx. So from that we can have the node, very important, as if the first two nodes. So let me out here the first node, number one, node number one, and node number two, and we are going to have the node number 3 and number 4 in here. So as you can see now, node number 3 is also important. Let's write down here. Number 3, it will be for delta m equal to v dx integral. So you can say that the change in moment equal to area under the shear curve. Shear curve, or the shear diagram. And then the number 4 that we have dm over dx equal to v dm over dx. Actually, that is slope of the moment diagram. So you can say that slope of moment diagram equal to the magnitude of v shear, right? Magnitude of the shear. So that two are the node for the moment diagram. Number 3 and number 4. They are very important. Very important. You need to master all of this before we go to practice here. So we have, as you can see, 4 nodes here that you need to keep in mind when you talk about the shear and moment diagram. How that change in shear diagram equal to the area under the load curve. The slope of the shear diagram equal to magnitude of the load. Similarly, the change in moment, area under the shear curve, and the slope of the moment diagram equal to the magnitude of the shear. So with that, we finish with the theory or the concept of the shear and moment diagram. In the next video, we show you a few examples, and then we go to the worksheet practice problem.